Okay, in this lecture we're going to cover the first part of our section 11.6 material on derivatives of products and quotients. So in our last section we had introduced a rule for differentiation called the sum difference rule, which said that the derivative of a sum or difference of two functions is equal to the sum or difference of the derivatives of those functions. So in this section, we'll consider whether or not the derivative of a product or a quotient of two functions is equal to the product of the derivatives or the quotient of the derivatives of those functions. And as we'll see pretty quickly, it turns out that that is not the case. So differentiating a product or a quotient of two functions is a little more complicated. So in this first part of our section, let's consider the following theorem known as the product rule, which will give us a method for finding a derivative of a product of functions. So here's what it says. If we have two functions f and g, which are differentiable, so their derivatives exist, then the derivative of the product f of x times g of x is calculated in the following way. So we first take the derivative of our first factor in that product, that is the derivative of f of x. And then we multiply by g of x. So the second factor we leave alone. We do not take its derivative just yet. And then we add the product of f of x. So we take our first factor, f of x, left alone, and multiply by the derivative of the second factor, g prime of x. So in English, this product rule says that the derivative of a product of two functions is found by taking the derivative of the first function times the second function plus the first function times the derivative of the second function. All right. So to see why this, or an example of why this rule works and why the derivative of a product is not simply equal to the product of the derivatives, f prime of x times g prime of x, let's consider the following example. So here we have two functions, f of x is x squared and g of x is x cubed. And in part A, we're told to find h of x, which is the product of f and g of x. So here, the function h of x is defined as x squared times x cubed. So recall properties of exponentials. If we're multiplying two functions which have the same base, this is the same as taking the exponential where we have the same base and we add the exponents. So 2 plus 3 gives us x to the fifth here. Now in part B, we're asked to then find the derivative of h of x. So the derivative of the product of f of x and g of x. Now in part A, we just found h of x is x to the fifth. So differentiating using the power rule, we would have 5 times x to the fourth power. Now in part C, we're asked to find individually f prime of x and g prime of x. So here f of x was x squared. So f prime, the derivative, would be 2x to the first power. And g of x was x cubed, so g prime is 3x squared. So then in part D, we're asked to find the product of the derivatives, f prime and g prime of x. So here, f prime of x times g prime of x is the product of 2x and 3x squared. So multiplying our constant terms, the 2 times 3 gives us a 6, and then our x to the first times x squared is x cubed. So in part E, we're asked to verify that the derivative of the product, f of x times g of x, is not equal to the product of the derivatives, f prime times g prime. So in our earlier work, in part B, we found the derivative of the product, f times g, is 5x to the fourth. So here, our left-hand side of the equation is 5x to the fourth for the derivative of f times g. And then we ask the question, is that equal to the product of f prime and g prime? Now in our earlier work, part D, we found the product of the derivatives, f prime and g prime, is 6x cubed. So our right-hand side of this equation is 6x cubed. And we can see that these two expressions are not equal to each other. So here in part E, we have shown that the derivative of a product of functions is not simply equal to the product of the derivatives of those functions. We have to make use of this product rule. So finally, in part F of this example, we're asked to verify that h prime, that is the derivative of the product, is equal to f prime times g plus f times g prime. So here, h prime of x in part B we found was 5x to the fourth. And we're asking, is this equal to the given expression on our right-hand side of this equation, which was f prime. So taking the derivative of f, we had 2x times g of x, which is x cubed, plus f of x, which was x squared, times g prime of x, which was 3x squared. So expanding our expression on the right-hand side of this equation, we have 2 times x to the first times x cubed would be 2x to the fourth, plus 3x squared times x squared would be 3x to the fourth. So we have 5x to the fourth is indeed equal to 5x to the fourth. So we see in this example that our formula that we had stated in the product rule is valid for these functions. And so that rule holds in general, not just for these specific functions, f and g. So now that we have this technique for finding a derivative of a product of functions, let's look at some examples. So in this next example, we are told to use the product rule to find the derivative of each function and simplify our answer completely. So in part A, we have the function y equals 2x squared plus 3 times 3x plus 5, a product of two polynomials. So making use of the product rule, let's say by the product rule, our derivative, y prime, is found by taking the derivative of the first function in our product. So here the derivative of 2x squared is 4x, plus the derivative of 3 is 0, so we just have 4x, times the second function in our product, which was 3x plus 5. Then we add the first function in our product, which was 2x squared plus 3, and multiply by the derivative of the second function in that product. So here the derivative of 3x plus 5 is simply the slope of that linear function, which would be 3. So this is an expression for the derivative y prime, but we're told that we have to simplify completely here. So let's expand these expressions in group-like terms to simplify. So if I distribute my 4x, I have a 12x squared plus 20x plus for the second part of this derivative, if I distribute my 3, I have 6x squared plus 9. So grouping like terms together, well, we had a 12x squared and a 6x squared. So altogether 18x squared. Then plus 20x plus 9. So this is our expression in simplified form for the derivative of that product. All right. Now, another way which we could have proceeded in this example for part A is as follows. If we were not told in the directions that we had to use the product rule here, we could have expanded our function for y and then differentiated the resulting polynomial. So if I expand the expression that we have for our function y, we have a 2x squared times 3x, which would give us 6x cubed, plus 5 times 2x squared gives us 10x squared. Then plus 3 times 3x is 9x, and then plus a 3 times 5 is 15. And now differentiating term by term using the sum difference rule and the power rule, we would have 18x squared plus 20x to the first plus 9. And notice that that is the exact same expression that we obtained by applying the product rule. However, this second approach would not be valid for this particular problem since we were told that we had to use the product rule in order to find that derivative. So let's look at another one. In part B, we have f of x is equal to 2x to the 7th plus x minus 8 times x squared minus 3. So the product of two polynomial functions. So using the product rule to differentiate here, we could say by making use of the product rule, our derivative f prime of x is found by first taking the derivative of our first function in the product, which would be 14x to the 6th plus 1 times the second function in our product, in this case, x squared minus 3. Then we add the product of the first function, which was 2x to the 7th plus x minus 8 times the derivative of our second function in the product. So here the derivative of that x squared minus 3 would be 2x to the first. So we have the following expression, but again in this problem we're told we have to simplify our answer completely. So let's expand and collect like terms. So for the product of these first two terms, if we expand, we have 14x to the 6th times x squared is 14x to the 8th minus 14x to the 6th times 3, which would be 42x to the 6th plus 1 times x squared is simply x squared, and then 1 times negative 3 is negative 3. Plus, if we, for the second part of our derivative, distribute this 2x term throughout this polynomial, we have 4x to the 8th plus 2x squared minus 16x. So our derivative, f prime of x, grouping like terms, well, we have a 14x to the 8th plus 4x to the 8th leaves us 18x to the 8th. And moving to our next term, we have a negative 42x to the 6th. Then grouping our x squared terms, we have a 1x squared plus 2x squared is 3x squared. And then lastly, our linear term and constant term are negative 16x minus 3. So here we have our expression for the derivative in simplified form. So let's look at one other one. In part C, we have the function g of x is equal to 5x squared plus 12x quantity squared. So here we have a function which is being raised to a power, and we'll consider how to approach this another way in our next section. But for now, in this example, we're told to use the product rule to find the derivative of this function. So let's think about this as a product. So here, if I have a function squared, I can think about that as the product of that function with itself. So now, g of x is the product of two polynomials, so we can use the product rule to find our derivative. So here, by the product rule, our derivative, g prime of x, is equal to 20, or the derivative of our first factor, or our first function in the product, which is 10x plus 12, times the second function in our product, which was 5x squared plus 12x. And then we add the first function in our product, which was 5x squared plus 12x, times the derivative of the second function in our product, which is 10x plus 12. So notice, in this case, that we have the product of 10x plus 12 with this 5x squared plus 12x. So since I was taking the same function for both factors in my product, it was a function being squared, I have the exact same expression when I'm taking the sum of these terms in the product rule. So I can rewrite this as follows. I have 2 times 10x plus 12 times 5x squared plus 12x. So simplifying, if I expand, I have a constant 2, and then expanding this product of 10x plus 12 and 5x squared plus 12x, I have 50x cubed plus 120x squared plus 60x squared plus 144x. Or distributing this constant factor of 2 out in front, I have 100x cubed plus within our parentheses, we've got 120x squared plus 60x squared. So that would be 180x squared, or when we distribute the 2 times 180 gives us 360x squared. And then plus our 2 times the 144x is 288x. So we have the following simplified expression for the derivative of this function. Okay. Now, in the next part of this section, we'll introduce a rule for differentiating a quotient of two functions. So here, just like we had a rule for differentiating products of functions called the product rule, we have the following theorem known as the quotient rule, which tells us how to differentiate a quotient of two functions. So here's what it says. If f and g are differentiable functions, so two functions whose derivatives exist, then the derivative of the quotient f of x divided by g of x is equal to the following. So it's first found by taking the product of the derivative of f, that is the derivative of the numerator, times g of x, whatever function is in our denominator. Then we subtract the product of f of x, so our numerator left alone, times g prime of x, the derivative of the denominator. And then that entire expression is divided by g of x, which is your denominator for the quotient, squared. So in English, the quotient rule says that the derivative of a quotient is given by the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. So let's look at some examples where we're making use of the quotient rule. So in this next one, we're told to use the quotient rule to find the derivative of each function and again simplify our answer completely. So in part A, we have y is 4x plus 11 over x squared minus 3, so a quotient of two polynomials. And making use of the quotient rule, let's say by the quotient rule, our derivative y prime is found by first taking the derivative of the numerator, which is simply the slope of that line, in this case 4, times the denominator, which was x squared minus 3. Then we subtract the numerator, which was 4x plus 11, times the derivative of the denominator, which would be 2x. And then this entire expression is divided by the denominator squared. So in this case, x squared minus 3 quantity squared. Now simplifying within the numerator, we could expand and group like terms. So for the first part of my numerator, if I distribute this constant 4 through my x squared minus 3, I have 4x squared minus 12. And then I am subtracting for the second part of our numerator. If I distribute this constant or this factor of 2x through to the 4x plus 11, I have 8x squared plus 22x all over the same denominator, x squared minus 3 quantity squared. So now grouping like terms in the numerator, we have y prime is equal to, well, we had a 4x squared, and then I'm subtracting 8x squared. So that leaves me a negative 4x squared. Then we had a minus 12 and a minus 22x. So I have negative 22x minus 12, and the whole thing is still being divided by x squared minus 3 quantity squared. So we have the following simplified expression for the derivative of this quotient. Now you might ask, well, why did we not expand this expression for x squared minus 3 quantity squared in the denominator? Well, the typical convention is the simplified expression for this derivative, you leave that denominator in factored form. That is, as the denominator of your original function, but squared. So let's look at another one. In part B, we have y is 6x minus x squared over 4x cubed plus 3. So again, as soon as we see that this is a quotient of two polynomials, we should think to ourselves, let's use the quotient rule. Additionally, in the example, we're told to use the quotient rule to find these derivatives. So using the quotient rule, our derivative y prime is found by first taking the derivative of the numerator, which would be 6 minus 2x, and then we multiply by our denominator, 4x cubed plus 3. Then we subtract the numerator, which is 6x minus x squared, times the derivative of the denominator, which is 12x squared plus 0, or simply 12x squared. And the entire expression is being divided by our denominator, 4x cubed plus 3, quantity squared. So again, to simplify, we can expand throughout the numerator and group like terms. A little bit later in the course, we'll see why this would be worthwhile. So if we expand the product of these two polynomials in our numerator, we have a 24x cubed plus 18 minus 8x to the fourth minus 6x, and then we are subtracting, if we distribute the 12x squared through to this polynomial, we are subtracting the quantity 72x cubed minus 12x to the fourth. And this is still all over 4x cubed plus 3 quantity squared. So finally, our derivative, y prime, grouping like terms. Let's start with the highest powers of x first. We have these two terms involving x to the fourth. So we had negative 8x to the fourth minus a negative 12x to the fourth, or plus 12x to the fourth, which would leave us 4x to the fourth. Then grouping our x cubed terms, we have 24x cubed minus 72x cubed. So that gives us a negative 48x cubed. And then lastly, our linear and constant terms are negative 6x and plus 18. And this is still all over 4x cubed plus 3 quantity squared. So this would be the simplified expression for the derivative of that quotient. So in these first few examples, we've seen now how to find the derivative of a product of functions or a quotient of functions. So let's consider an example where we might have to make use of both rules within the same problem. So in this next one, we are asked to find the derivative of the function f of t, which is a quotient of two polynomials, where our numerator is a product of two functions, and simplify our answer completely. So here, in order to differentiate this function, well, we see f of t is a quotient of two terms. So we'll start by using the quotient rule. So here I'll say by the quotient rule, our derivative f prime of t would be found by first taking the derivative of the numerator. Now, our numerator is a product, so we're going to have to use the product rule to differentiate that. So for right now, I'm just going to write the derivative of the numerator using the Leibniz notation, d over dt, so the derivative with respect to t, of our numerator, 8t minus 3 times 4t plus 5. So that is the derivative of the numerator times our denominator, which is 2t minus 1. And then we subtract the numerator, which was 8t minus 3, times 4t plus 5, and we multiply by the derivative of the denominator. So here the derivative of the linear function in the denominator is just the slope of that line, in this case 2. And then the entire expression is divided by the denominator, which was 2t minus 1 squared. So now, in order to move forward, we need to find the derivative of this product, which appears in our numerator. So by the product rule, we have our derivative, f prime of t, is equal to, well, let's differentiate that product that we had through the numerator. So recall the product rule says you first take the derivative of the first function in your product, so in this case 8, times the second function in the product, 4t plus 5. Then we add the first function, 8t minus 3, times the derivative of the second function, which was 4. So that is the derivative of this product which was appearing in our numerator. Now recall that entire expression is then being multiplied by 2t minus 1. So we then multiply by 2t minus 1, and then we are subtracting the remaining terms, which were 8t minus 3 times 4t plus 5 times 2. And still, all over our denominator, 2t minus 1 squared. So now let's start simplifying. We're told to simplify our answer completely here. So within these square brackets in the numerator, expanding, we have a 32t plus 40 plus 32t minus 12, all times 2t minus 1, minus, if we expand the product of 8t minus 3 with 4t plus 5, we have 32t squared plus 40t minus 12t minus 15, which is then all being multiplied by 2. And still, all over our denominator, 2t minus 1 squared. So now, within our square brackets in the numerator, if we group like terms, say the 32t plus 32t, we have 64t, and then grouping our constant terms, plus 40 and minus 12, we have plus 28. And this is all being multiplied by our 2t minus 1. And then we're subtracting, if we group our like terms within this set of parentheses, we have a 32t squared. Grouping the factors of t, we had a 40t minus 12t, which leaves us the positive 28t, and then minus 15. And this entire expression is still being multiplied by a factor of 2. And all over our denominator, 2t minus 1 squared. So now, expanding all products through the numerator, taking the product of these first two functions, we have 128t squared minus 64t plus 56t minus 28. And then we are subtracting the quantity if we distribute our 2 throughout this polynomial, we have a 64t squared plus 56t minus 30. Still all over our 2t minus 1 squared. So finally, grouping all like terms based off the power of t in our numerator, we have a 128t squared minus 64t squared. Leaves us with 64t squared. Then grouping our powers of t, we had negative 64t plus 56t, and then we are subtracting on the end 56t. So the plus minus 56t will cancel, and we're left with negative 64t. And then grouping our constant terms, we had a negative 28 minus a negative 30, or plus 30, leaves us with a constant of positive 2 all over 2t minus 1 squared. So here we have a simplified expression for the derivative of this function. So in this lecture, we've introduced the product and quotient rules and seen a few examples of how we can use the product or quotient rules to differentiate functions which can be thought of as a product of two functions or a quotient of functions, or as we saw in this last example, perhaps combining the rules if we have a quotient of products of functions.